Okay, so today, right, lecture 14 is going to be about how to actually solve the finite difference equations for the two-dimensional heat equation. So the 2D finite difference solution. So during the last lecture, we went over how you turn an equation that looks like this right? The 2D steady heat equation with no generation. We'll turn that into some system of simultaneous equations that we defined on a grid or a mesh composed of a series of nodes. Right, so the idea was we took our two-dimensional domain that we're trying to solve this equation on, we split it up into pieces, and we said, hey, at every intersection of one of these lines, we have what we call a node. So we have interior nodes, and we have boundary nodes. Okay, so this would be considered a mesh that has 5 by 5 nodes or 4 by 4 segments. Okay, and the idea was that we could use these things called finite differencing equations to write, instead of this second-order partial differential equation, we could pick a node. So, for example, let's pick this guy right here. Okay. And we could write that if we call this node 2, we call this node 2, 1, or rather 2, 2, we'll call our differential equation would be written instead as a series of summations. So 2 to 1 plus t 1, 2 minus 4 t 2, 2 plus t 1, 3 plus t 3, 1 is equal to 0. And so this is an expression of this equation, but written only at this point. And we do it by looking at the 4 surrounding sort of neighbors, if you will. So it's looking at the points that are next to it and sort of doing an approximation of the derivatives and saying that the sum of the derivatives is equal to 0. So the idea is, in a mesh like this, we would have 9 unknowns, right? 9 nodes on the inside where we don't know the temperature, and we would have, I guess in this case, 18. Yes, 18 nodes around the outside where we do know the temperature that are on the boundary. Okay, and so the idea is we would write an equation like this for each one of these unknown nodes. We would get a set of 9 simultaneous equations that are all different to solve for these 9 unknowns. Right? That was the gist of the last lecture. Today we're going to focus on the more practical aspects. How do you actually make this happen? Right? We don't want to have to write this out and solve the system of equations by hand, because the idea with numerical methods is typically to solve them on a computer. And we want to be able to solve this instead of for a measly 5 by 5 node system. We want to be able to crank this up to 100 nodes in each direction. In which case we're going to have 10,000 minus the number of boundary nodes. It's not a system of equations you want to write out by hand and solve. So, as I said, today's focus is on implementation. And this is something where the book falls a little bit short, right? It tells you, it gets you this far, and it'll give you equations that look like that, and it'll give you equations that are in this form that deal with convective boundary conditions and adiabatic boundary conditions, etc. But it doesn't really tell you how to systematically approach the problem if it's more than a couple of nodes. So what we're going to be doing is, I'm going to be teaching this sort of from the standpoint of someone using MATLAB. Right? That's what I think is probably the easiest coding language to approach problems like this. And a lot of what I'm going to be talking about is sort of mirrored in the homework assignment that I posted, right? So the homework assignment's a little bit, the flavor of it's a little bit different in that it's only 2 problems. The first one's a super simple shape factor problem. So it's pretty much look up something in a table, use it to calculate heat flux or heat rate. Problem number 2 is going to be solving a problem like this, but for mesh sizes of like 5 by 5, 10 by 10, 50 by 50, and 100 by 100. So you're going to have to come up with a method to program this and have the computer solve it for you. And so the problem is structured as sort of a tutorial walkthrough, but with some gaps there that leave some things that you have to figure out, mostly in terms of how you're going to implement something in MATLAB. So we're going to be trying to fill some of those gaps in lecture today, and then the homework should walk you through the conceptual steps. So the idea here is first, so clear this. So step 1 with a problem like this. Let's say you're given, right? You're told, all right, here's a domain, square, and we know the temperatures on the boundaries. So similar to before, we would say that right at the bottom here we have a T south boundary, T east boundary, T north boundary, and T west boundary. And we're asked to solve for the temperature distribution inside the interior of this square plate. All right. So step 1 is going to be define the way you're going to chunk this plate up into pieces. All right. Numerics is all about what's called discretization. So we have to pick that discretization first, and we'll work from there. So step 1 is define your discretization. And what this means is pick how many segments you're going to break it up into, or how many nodes you're going to put in each direction. So we're going to walk through this whole problem doing a process that involves a 4 by 4 node arrangement. So we would say here's a node, here's a node, here's a node, here's a node. So once again, we would say that this is a 3 by 3 segment mesh, okay, or 4 by 4 node mesh. So there are a total of 16 nodes, and because we've defined the boundary conditions, right, we already know 12 of those. So we really only have 4 unknowns that we're dealing with on the interior, those interior 4 points. Okay. So this translates into define your number of nodes, and we'll call this nx and ny. That is the number of nodes in the x and the y direction. So in this case, we have nx equals 4 and ny equals 4. This is also a good opportunity to, it'll be helpful later when you're plotting results if you create sort of a matrix that describes like the x and the y positions of each node. So from this, if you create an x and a y matrix such that xij is the location of node ij, and ditto for y. The idea here is that you should have, in this case, on a 4 by 4 matrix, right? Just has different x and the y positions. A useful function in MATLAB to do this step is it's called mesh grid. You should look up the documentation for it, but it's a really nice function. If you just say my x nodes, you say that the x's are at, let's say this has a width of 1. You'd say that my x nodes are at positions of 0, 0.25, 0, 0.33, 0.67, and 1. Okay. And same with y. You'd say y has values of 0, 0.33, 0.67, and 1. And then you feed those two lists of positions into mesh grid. It'll make a matrix of x and y positions. So it'll say, x, this x vector will just say 0, 0.33, 0.67, 1, and it'll repeat that as it moves down the rows. Okay. And then for y, it'll be the opposite. The y positions, all of these will have the same values. Those will be stepped up at 0.33, the next one up at 0.67, so on and so forth. This will be useful mostly for plotting later on. Okay, so when you're actually spitting out the results in a graphical form, you need to tell MATLAB what the x and the y position, as well as the temperature of each node is, so that it can create a sort of a heat map or a contour plot. But anyway, this is more, it doesn't have much to do with the actual solution process. So then we can define, right, delta x equal to, we'll say that this is Lx is the width of this whole thing in the x direction, divided by nx minus 1, and delta y is equal to Ly divided by ny minus 1. And for the purposes of this problem, right, and what we're doing in this class, we're going to assume that we always are working with a situation where delta x is equal to delta y. That makes the math easier. So we're going to assume that these two quantities are equal to one another. All right. We're going to take a step back, right? Before, when we described like how we would set up conceptually the system of equations, we basically we only wrote those equations for the interior nodes, right? We defined our numbering starting at the first unknown node. That's fine if you're going to solve something by hand, but when we're doing it in the computer, it's easier to proceed to begin with, considering all of the nodes. And so rather than starting the numbering at this point, we're going to start the numbering at the first node, which is at the boundary. So once again, we would say that then this node is 1, 1, right? This is 2, 1, 3, 1, 4, 1. This would be 1, 2, 1, 3, 1, 4, 2, 2, 3, 2, 4, 2, so on and so forth. Likewise, remember, that's what we call indicial notation or IJ notation. Alternatively, and something we're going to have to do also is to number these just in ascending order. And so for this purpose, we're going to go ahead and start counting across in rows. So this will be 1, 2, 3, 4, 5, 6, 7, 8. 1. I'll write those numbers in blue so that they're distinct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, and 16. This all seems a bit mundane, but this is going to save you a ton of time later, is if you're careful in laying out how you number things. Next step is to create what I'll call a node location table. All right. So what this is basically a way of mapping our IJ notation to a numbering scheme, to the ascending numbers. This n notation. So create node location table, which will essentially be a column that have n. You have a column that says I and a column that is populated by j. So the idea here is, right, n is going to, let me go ahead and quickly just draw these again. So if these are our nodes, we've got 1, 1, 2, 1, right, 4, 1, 1, 2, and we're numbering 1, 2, 3, 4, 5, all the way up to 16. It's very easy to build this for any type of grid size because you're going to make an n column that's just 1, 2, 3, 4, 5, 6, right? Counts down to 16. And then an I, right? For every, in this case, the I counts up 1, 2, 3, 4. So it's an ascending vector for the number of nodes in the x direction. So there's a group size here, 1, 2, 3, 4, that is the length nx, right? The number of nodes in the x direction. And at the same time, the j for all of those stays constant. 1. And then this steps up to 2, and this resets. 2, 3, 4, 2, 2, 2, until you get all the way down to 4, 4. So the way you want to build this in MATLAB is to basically do it in pieces, where you're going to assemble it in blocks that are nx in length. Okay, so you're going to use a for loop, and you're going to say step through. Right there, each block is nx in length, and there are ny number of blocks. Okay, because it's going to step through all of the y indices and stack those up on top of one another. And so the advantage of making this table is, let's go ahead and fill it out the rest of the way because we're going to use it. 7, 8, 9, 10, 11, 12, 13, 15, and 16. One, 3, 4. 1, 2, 3, 4. 3, 3, 3, 3, 3, 3, 3. That should be 4. Yep, sorry. 4. Okay. So hopefully, right, the utility of this table is apparent. The idea is if you have a T or something located in the matrix form, you can look up ij and match it up to the associated node number. So by building this table beforehand, it becomes a lookup table. Or if you are working in n notation, right, and you say, let's say you've solved for temperature number 9, but you want to know where you put it back into the matrix in order to plot out your results, there's your ij values. So this saves you the trouble of having to build it on the fly every time you want to change form. Okay. It also makes it easier for you to assemble what we'll call a boundary node table. So we'll call this node underscore locations. We also want to build a table of boundary nodes. And so the idea here is you're going to, based on your I and j values, if I is equal to 1 or the highest value, the lowest or the highest value, that means that it is either at, right, the left or the right-hand side, meaning it's on a boundary. Similarly, if j is at a value of 1 or 4, that means it's at the top or the bottom. That means it's also on a boundary. So the idea here is that this table allows you to search out the value of n for all nodes on a boundary. So what you're going to do to build your boundary table is n, and then over here you're going to put the temperature, the known temperature at that boundary. So in this case, right, our boundary nodes consist of 1, 2, 3, 4, right? All those that have j equal to 1. anything that has I equal to 1 or 4 also goes in there. So we've got 5, 8, 9, 12, and then 13, 14, 15, 16. And because we've defined the temperatures at each of these boundaries, right, we've got T east boundary, T north boundary up here, T west boundary, and T south boundary, we can go ahead and use the information about I and J at each of these points to fill in what the temperature is. So for node 1, for example, at this lower left-hand corner, this is kind of an oddball because, right, it's at the meeting point of two boundaries. It's at both on our southern boundary and our western boundary. So there are lots of ways of dealing with this. My preference is just to take the average of the two temperatures wherever you're at a corner. Okay. So here we would say it's T south boundary plus T west boundary over 2, right? And then for 2, 3, 4, 2 and 3 are on just the south boundary, T SB, and then T SB plus T east boundary over 2. 5 is just T west boundary, T east boundary, west boundary, east boundary. 13's on another corner, so it's going to be T west boundary plus T north boundary over 2, NB, T NB, and T NB plus T east boundary over 2. What I would suggest doing for this is essentially go through and like do a loop, that says if I equals 1, right? Then assign it a value of whatever T west boundary is. If I equals whatever your nx value is, meaning it's at the far hand side, assign it a value of T east boundary. Same for J, south boundary, north boundary. Then once that table is made, go back through and use another for loop and say, if I and J are equal to 1, then combine. So that way you only have to make 4 sort of tweaks to your matrix. The idea here is to make it flexible because you're going to have to do this for a bunch of different values of nx and ny in the homework. Okay. So it helps to come up with sort of an automated process for building these tables that can extend to grid sizes larger than this. And then finally, we're going to make just a list of the interior nodes. So this is essentially, if we take this vector and we eliminate all the ends in this vector, then what we have left over are the interior nodes, which are, in this case, 6, 7, 10, 11, right? And we have 6, 7, 10, and 11. And thing is here, we don't yet know the temperature. So just leave it as a column vector. The idea with making these 3 tables is, again, this allows you to go back and just sort of do a lookup approach rather than having to recalculate your meshing stuff on the fly. Everyone caught up on these? Can I? Okay, so next step is to use the information we've assembled here to construct our coefficient matrix, it's called. So the idea is now, if we go back up to what we did here, right? This is, it's a linear summation of different temperatures. Some of them are known, some are unknown. But each one is led by a coefficient. In this case, it's 1, 1, -4, 1, 1. So what we're going to do is assemble a vector of t's and then a matrix that contains all those coefficients and express this for for all of our unknown nodes using a matrix or a linear algebra expression. So once we have those tables, we're going to move on to create our coefficient matrix. Okay, so the idea is, let's go ahead and paint again this picture of our grid. And let's say, once again, that we want to, let's say we'll pick this center point here, this green one, and say that we want to write the finite difference version of the heat equation at that point. The way we would do so is, right, by saying if this is ij or n, we're not going to, right, obviously this is 0.33, but this is in general. We would say that, right, t I plus 1 plus t j plus 1 minus 4t, I plus 1 j, and that should be I and j plus 1, t j plus t I minus 1 j plus t I j minus 1 equal to 0. So we can, in general, right, without defining where this is, we can, using our node location table we assembled before, we can define where the n value of each of these temperatures, or of each of these indices. So we could say that I, right, if ij is equal to, or leads to n, okay, which we would get from looking up here, looking up our ij values. I plus 1 j, I j plus 1, I minus 1 j, and I j minus 1 would lead to, in this case, so ij is n, I plus 1 j would mean the one to the right. Okay, so this is just going to be n plus 1, right? ij plus 1 means the one above it. So this is going to be n plus 1, 2, 3, 4. In other words, it's going to be n plus 4, or n plus, little n plus nx, right? The number of grid points in the x direction. I minus 1 means one to the left, so this is going to be n minus 1. And then j minus 1 right below. So similarly, this is going to be n minus 4, or more generally, n minus nx. The reason that we like this is because this allows us to write, for example, this, the finite difference equation at this point as t, right, t n minus nx plus t n minus 1 plus t n, minus 4tn. Erase. tn plus t n plus 1 plus t n plus nx equals 0. Okay? This is the same expression here. So we can write this now as, if we have t1, let's say we have t1, t2, t3, t4, t5, t6, t7, 8, t9, 10, t13, 14, 15, t16. Right? The idea is we could write our t's in this column vector, and if we want to, for example, write the finite difference equation at n equals 6, okay, then what we would do is we would say n is equal to 6, so n minus nx would be 2. We'd say 0, 1, 0, 0, 1, negative 4, 1, 0, 0, 1, 0, C, 0. What is this multiplication of a column vector by, of a row vector by a column vector give us? Well, it's 0 times t1 plus 1 times t2, 0 times t3, 0 times t4, plus 1 times t5, minus 4 times t6, times plus 1 times t7. The idea is this is recreating the same expression we wrote before. Okay, so this will give us t, in this case t2, plus t5 minus 4, t6 plus t7 plus t10. Right? 2, 4, 6. Yep. Which is our finite difference expression at point number 6, which means that this is equal to 0. So rather than writing our system of equations, equation by equation, it is we can instead write it in a vector format where each row we could write then another column here, another column here, another row there, okay, that are filled with coefficients, and what that is going to lead to our system of equations. Or we can simply do away with this idea of writing them separately and write it as one big matrix, right? So we're going to write some big matrices up on the screen here and talk about what to do with them next. So in the end, right, if we have 4 unknowns, our coefficient matrix should ultimately be what? It should be, if we're going to solve it, it has to be square, right? If we're going to be turning this into something, this looks like this. A times t is equal to b, right? And so the way you solve this is what? T equal a inverse times b, and for this to be possible, right, to be able to invert a matrix, it has to be square. So what we're gonna do is, if we set up the equation, the system of equations by hand, this would be easy to do, but that's not scalable. So we're going to use the computer to create this big matrix, and then we're going to chop the chunks out that we don't need in order to make it the 4x4 matrix that we can solve for our unknowns. So I'm going to go ahead and write out our temperature vector one more time here. 4, 5, 6, 7, 8, 9, 10. And so the idea is we have, right, if we've got the node numbers over, oh, come on, there we go. I want to move this up here, and I want to move this over a little bit. If we write the node numbers, okay, 4, etc., we know that the only ones that we actually want to solve at are this 6, 7, right, 9, 10, 11, and 10, 11. So in other words, this is unknown, this is unknown, this is unknown, this is unknown. So if we write our system of equations out at just those nodes using this matrix form, what we're going to end up with is something that looks like this. 0, 1, 0, 0, 1, negative 4, 1, 0, 0, 1, 0, 0, 0, 0, 0. At 7, it's just going to be shifted over by 1. 4, 1, 0, 0, 1, 0, 0, 0, 0. At 10, right, it's going to start at 0, 1, 0, 0, 1, negative 4, 1, 0, 0, 0, 0, and at 11 it's going to be shifted over 1 relative to that. 1, 0, 0, negative 4, 1, 0, 0, 1, 0. So those are the only 4 equations we really need. Okay, but it's a bit of a pain to have MATLAB loop through and only build these 4. What's much easier to do is recognize that if we were to fill in the rest of these equations as well, you know, for the rest of the nodes, which we don't need to do because we already know the temperatures there, what we would end up with is this system that has constant elements in a diagonal pattern. So it's a repeating and shifting pattern of coefficients. Right? 1, 1, 1, 1, 1, 1, 1. And I won't draw the whole thing, but essentially it's this stencil of 1, 0, 0, 1, negative 4, 1, 0, 0, 1 that's just shifting and repeating, heading to the lower right. Yes? Because that's right. So if right, exactly. That's how we. It's going to change if you have a different number of nodes, right? So if, for example, if we had 5 nodes instead, then the idea is that like this is where the negative 4 is. That's multiplying by whatever node we're trying to solve at. Okay, so for index 6 here, this is saying that at node number 6, which would be right 1, 2, 3, 4, 5, 6 at this location, it's saying that to look at the neighbors, we have to to go over left 1 in order to go I minus 1. We have to go n minus the number of grid points in the x direction. So it's simply counting backwards the number of points it has to go. And so if we have 1, 2, 3, 4 between the point we're looking at and its neighbor below, that reflects the fact that we have 1, 2, 3, 4 here. And so if you were to make it 100 by 100 grid points, the idea is that these would be 100 elements apart. It would be 1 and then 99 zeros. And then 1, negative 4, 1 to go to the ones to the left and the right. Then 99 zeros and then a 1. So it's a little bit hard to visualize. I get it, but honestly, you guys may not feel the same. But I think numerical methods like this are kind of they're both extremely common. So it's very good to know how how these things work. But also, I find problems like this kind of fun. It's a big jigsaw puzzle, right? You're trying to piece together the problem in a sort of reminiscent of Sudoku or something. So anyway, so we're going to take advantage of the fact that it's this repeating pattern, right? And like I said, rather than telling MATLAB creating this sophisticated sort of like if-then loop, we're going to create this entire matrix, and then we're going to shave away the pieces we don't need to leave behind just these 4 equations for our 4 unknowns. So the easiest way to do this is using a MATLAB function called Toeplitz. And this gives us a Toeplitz matrix which has constant diagonals. It's essentially it's constant diagonals and it's symmetric, which exactly describes this matrix here, right? It's symmetric about the diagonals filled with negative 4s. And so the easiest way to do this is you have to create the first entire row of your matrix. You have to figure out what part of this pattern looks like. So if we were to look up at this first row, we would see that, right, the -4 goes all the way to the left-hand side. Right? It starts with -4, 1, 0, 0, 1. So there's our moving to the right by nx, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. We have to come up with this first row. And so essentially what this means is we have to look at this first element and say, let me create the stencil to make it look at this point and to make it look at this point. And what it's going to do then is it's going to shift it over and it'll fill in. So it'll create the matrix that essentially loops through each node, and as it moves into the inside of our mesh, it'll add in the points over here and here. So if we define first row, and here's a quick way to make that, right? First row would be equal to, for example, right, -4, 1, and then the command we would give MATLAB would be zeros, 1 tall, and how many wide in this case. If we want to move over nx, right, go 1, 2, 3, it's going to be nx minus 1, right? Or sorry, nx minus 2. Nx minus 2, 1, and then zeros, the total number of elements minus the number we've already entered in here. So it's going to be nx times ny minus, and then we've got to count up. We've got 1, 2, 3, and then nx minus 2, so it's going to be nx minus 2 minus 3, so nx, those negatives are going to cancel out, nx plus 1. And so what this is going to do is it's going to spit out a vector that looks like this right here. Let me make sure I gave you that. Yep. Okay. And then you're going to say that A is equal to Toeplitz of this first row. And it's going to spit out this big square matrix that is, in this case, right, it's going to be this entire thing. It's going to have a bunch of zeros. It's going to have these diagonals, a bunch of zeros, and it's going to be 16 by 16 for this problem, or the number of elements or number of node points you have by the number of node points. So if you do, if you're doing a 100 by 100 mesh, okay, so 100 grid points in the x direction, 100 in the y direction, this matrix is going to be not 100 by 100, but 10,000 by 10,000. Okay, so this is why it helps to have these functions that spit it out very quickly and save you the trouble of trying to put it together by hand. So then what we're going to do, right, so I think this is going to be sort of a two-part implementation. We'll finish it up on Monday. But then what we're going to do, right, is in order to shave out all of the crap we don't need, right? We don't need any of these equations that correspond to n values that are on the boundary, because we already know the temperatures there. So what we're going to do is go back to this table we made, our boundary nodes table. We're going to take this vector, right? So 1, 2, 3, 4, 5, 8, 9, 12, 13, 14, 15, 16. And we are going to remove or delete all of those rows from our matrix. So it goes 1, 2, 3, 4, 5, 9, 12, 13, 14, 15, 11. So what it's going to leave us with then is, I'm going to go ahead and copy
never mind, it's not going to let me copy that. Oh, it did. Nice. Because we're going to be left with this sort of, this much smaller now matrix that is, oops. So now it's going to be n, right, the number of interior nodes tall, and it's going to be nx times ny wide.
Okay, so this still isn't a square matrix, meaning we still can't invert it. Right? But understand what this is doing. This is our system of equations that are unknown nodes. Okay? It's just written with a bunch of these needless zeros, you know, that mean we're writing it in terms of a coefficient times every single other node in the mesh. So the next thing we're going to do is basically what happens when you've got,
let's say we've got, very simple example here, x plus 3 is equal to 0.
Right? Very easy to solve sort of mentally, but what we're doing when we mentally solve it is what? We take our known value, we move it over to the right-hand side, and we use it to solve for our unknown. Okay, we're going to do a very similar thing here, but in order to move things over to the right-hand side, right, we've got to acknowledge which nodes we know something about. So all the ones on the boundary with the known temperatures, we are essentially going to loop through.
So we have 1, 2, 3, 4. Actually, let me not write 1, so it's going to be confusing. We're at boundary, 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 boundary. Oh. It's not quite right. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 14, 16.
Okay, yeah, there we go. So the idea here is all of these, right, every column here that has a B under it is being multiplied by one of the temperatures we already know. And so what we're going to do is take all of those columns, multiply them by those respective temperatures, and move them over to the right-hand side. Because right now we've got this whole thing is equal to 0, 0, 0, 0. Right? This is our set of governing equations. So instead of zeros, we're going to call this over here B. We're going to loop through our boundary nodes table. So for all n that are inside that, right, n on the boundaries, we're going to say then that B is equal to B minus that corresponding column of n times that temperature of n. So what you're going to do is you're going to look up here at this table, and you're going to step through, use a for loop in MATLAB, and step through row by row. And you're going to say, here's my value of n. Make a copy of that corresponding column in A, or of A. So in this case, it's going to be, right, all these zeros. And you're going to multiply that by, right, we know T1. It's going to be the average of the T south boundary and the T west boundary. So over on B, you're going to have then B minus 0, or sorry, 0, 0, 0, 0 times T west boundary plus T south boundary over 2. Then you're going to move on to the next row of your column, or of your boundary table. So now we have one that actually has a 1 in it. Minus
1, 0, 0, 0 times, and then we know the temperature at node 2 is going to be T south boundary.
I think that wraps up time. Sorry, we'll finish talking about this on Monday, but take a look at the homework because, like I said, it's basically it's without the narration, but it walks you through a lot of these steps, and so probably with what you've got now, you'd be able to do the homework. So give it a crack. These types of problems are actually a lot of fun. So. Huh?
Do you have the other homework?
Oh yeah, so I've got homeworks that have been graded here. I'm going to go ahead and leave them on the table here. I blanked out the scores written on them so that you guys can look through them without me getting in trouble for FERPA. So feel free to search through those for your assignments. I'll plan on bringing those back each lecture so that if you don't get a chance to pick them up now, you can do them later.
Homework with you next Friday.
Yes.
The first question we are looking for